We're continuing to talk about Fourier analysis and the representation of signals, especially in the signal processing context, in terms of Fourier modes and the power of that representation. So if you're going to commit to using these Fourier modes, which in fact is pretty common because in fact in the last lecture I showed that these were in fact the eigenfunctions of linear time invariant systems, then we want to learn some of the properties and some of the necessities we need in order for this representation to work. So in particular, one of the things that we want to know is under what conditions does this Fourier representation actually converge? So we typically say something like where we have x of t is now going to be represented as an infinite sum of exponentials. And of course, if you're summing things over infinity, right, an infinite number of times, you want to make sure that there is in fact convergence of this series, okay? Where each of these a of k, here's the representation of this. And of course, we derived this in the last lecture, and now we're just asking questions about mathematically, if I use this infinite series, do I have any issues with convergence of this sum that we have to actually use to represent a signal? Of course, in practice, right, we never, in an algorithm, go from negative infinity to infinity. We go from some very large negative n to n, and but we still want this idea of a convergence to hold. So like when I do large n, I still get this thing to converge to a solution uniquely. And so I want to be able to figure out some of the conditions under which that holds. So the first condition is this idea of finite energy over one period. So it's called being absolutely integrable. So we're going to take a signal. So for us to use this Fourier representation, the absolute value of the signal squared integrated over one period has to be finite, so less than infinity. So this is a pretty simple condition. You can imagine if I had an infinite signal and I was trying to integrate over it, it's going to be a hard way to represent something that has an infinite amount of area under the curve. So it's just but here this is basically constraining it to have an absolute integrable term. Okay, finite energy over one period. That is the way to state this constraint. So that's the first one, and it's kind of obvious, and it has implications. And the implications are, when we look at the Fourier coefficients, here's a of n is equal to 1 over t, 0 to t, projection of xt into these Fourier modes. So when we do this projection, we want to make sure that the a of n actually are finite. Now, if there's finite energy here, I can just take the absolute value of both sides. So the absolute value of a of n is less than or equal to, I took the absolute value inside of that integral. The absolute value of this complex exponential is just 1, so this results into just this condition here, which is exactly where I said it has to be absolutely integrable, so this is bounded. So in other words, it's less than infinity, and so what you end up with then is each Fourier coefficient is also bounded. So when we come back to this representation then, what it's saying is this is finite amount, so you can't have anything going to infinity provided this signal is absolutely integrable. Okay, so that's how we get to that. There are two other conditions. We won't go into detail here, but I'll just explain what they are. Is that a signal, x of t, is of bounded variation. So there's a finite number of minimum and maxima. So you can't just have some signal that oscillates in an infinite number of times, but it has some finite amount of minimum and maxima. That's a condition here. Otherwise, you get into problems with trying to compute an integral if you have an infinite number of oscillations, let's say, in a finite period. Also, you only have only a finite number of discontinuities. Okay, so finite number of discontinuities means that you can have jumps in your solution. In other words, you can actually have a solution with a discontinuity, and the Fourier representation handles that, but you can only have finite number of them. You can certainly construct some very crazy functions where there's an infinite number of discontinuities, and that is beyond the scope of what a Fourier representation can handle. Okay, so here's the idea. Those are the conditions under which this Fourier representation holds, and so what we want to start looking at is thinking about it as a coordinate system and what it's going to allow us to do. So first of all, I just want to highlight this idea. It is a coordinate transformation. So I'm going from the original signal x of t, And when I Fourier transform this, I'm trading it out to coefficients of some Fourier modes. So the A of k is telling me it's the coefficient in the e to the I k omega naught t. So this is telling me the A of k, in other words, telling me how much to go in each of the directions. So another way to say it, if you have a representation in terms of Fourier modes, like cosine t, cosine omega 2t, cosine 3t, this A0, A1, A2 would tell you how much cosine 0t, how much cosine 1t, how much cosine 2t do you have in representing this signal x of t. So this is a coordinate transformation from your original time domain to a frequency domain picture where these are now the coefficients of each of the frequency components. Okay, that's the basic idea of a Fourier transform. Okay, so first of all, we have linearity. Exceptionally important property. We're going to be dealing with LTI systems, so of course we need this to hold. So if I have a signal x, which can be represented as A of k's, and y, which can represent a b of k's. These are the coefficients of the Fourier modes. And by the way, you can go from those Fourier modes back to the signal just as easily, right? This is a reversible transform. Then some signal z of t here, if I have ax plus b, and this is supposed to be a y of t, then the coefficients of c of k, which are the coefficients of the z, are just a linear combination of a times the coefficients a of k plus b coefficients b of k. Okay, so linearity, important property, it holds right here for us in this system. You also have a time shifting property. So if I take a signal that has a t minus tau, in other words, it's shifted in time by t naught, then I can actually make a change of variable here. I can shift all the time dynamics so that this x of t minus tau becomes, let's say, x of tau, and then it shifts then the exponential up here, which I can pull out part of the exponential, and this is what I get then. So if I had an original signal x of t with coefficients a of k, then the b of k coefficients, which are this time-shifted signal, actually pick up this exponential factor here, e to the minus I k omega naught t naught. Okay, so t naught is the time shift. So you get a phase factor. So this essentially creates a phase shift in your signal if you have some kind of time delay or time advancement, some kind of time shifting that happens in your process or signal. Okay, so that's a really simple thing to take care of in this context. So if I have, again, original signal x of t, which has this representation a of k, then if I have a time shifted signal, it's going to give me back out this exponential here that I'm pointing to, right? It gives me this phase shift times the a of k. So all I have to know is really the time, the Fourier coefficients for one signal a of k, and if I shift it, I just pick up this exponential piece that goes along with it. Okay, time reversal. I can take a signal x of t, and here it is, represented in Fourier modes. Then if I reverse time, in other words, t goes to minus t, then what that does, it switches the sign here. T goes to negative t, just pulls out a minus sign in front of this. So one way to think about it is this x of minus t is just actually producing for us, because of this negative sign, it switches a of k to a of minus k. So pretty nice, right? So time reversal just says the kth coefficient is now the minus kth coefficient and vice versa. So that's a nice little simple property for time reversal that happens. Time scaling, if I take x alpha t, the alpha t comes up here in terms of the time itself. And now what happens is, the only thing that happens is now instead of having an omega naught, I have alpha omega naught. So what it does is it fundamentally shifts the fundamental frequency, or the fundamental period t. Okay, so if I work in this new time-scaled version of the signal, the fundamental frequency shifts for us. Okay, and that kind of makes sense. So x of t and x of 2t, you basically took your signal, right, and x of 2t, and made it half as long. So the period shrunk by half. So that's what's happening here. That's what you see here. Okay. Multiplication, if I have two signals, y of t and x of t, and they have this representation in the Fourier domain, then if I multiply these two signals together, In the Fourier domain, let's call it h of k, this new signal, which is the multiplied, it is just a product across all the frequency terms get multiplied together to produce this sum here over all the coefficients of the Fourier modes. So it mixes all these frequencies together, and you have to basically produce this product here to give you the frequency cross the multiplication of these two signals. Finally, conjugation. If I have a signal x of t with a of k, the complex conjugate of that, you can calculate it out. That'll give you a of star minus k. In other words, the i goes to minus I, so that's this, well, switches the k to minus k. And if this coefficient a was complex, if a complex conjugated, it becomes a star. Okay? So this is sort of the conjugation. And with this conjugation, we can actually have then a condition for having real signals. And real signals we already talked about in the last lecture. The real signals are when this a of minus k is equal to a star k. If this condition holds, then what you know you'll have is this x of t signal here is in fact real. So these are all these properties we want to understand and work with. And the final one is Parseval's identity, which tells you that if I integrate this signal, x of t, the absolute value squared over a period, it's equal to the sum of all the Fourier coefficients, the square of the sum of the absolute value. This is a really important identity, and it's used commonly throughout Fourier analysis as a very convenient expression, also oftentimes to getting bounds on signals and bounds on energy, and just get fundamental understanding of signal processing. Okay, now what we're going to do is we're going to work with some code here. I have both Python and MATLAB, and I want to start digging down on this fact that signals, in fact, are orthogonal. So what I've decided to do, I'm going to write two codes here. They're very simple. One is the Python code. I first bring in some very basic things, import NumPy, some plotting, SciPy. Some of these you don't even need. We're not even using the FFT yet. But what I'm going to do is make a signal. I'm going to take a signal, NP linear space. I'm going to make a linear space that goes from 0 to 2 pi in n points. So chop it up into 200 points. So that's my domain x. It's over 2 pi. Chop it into 200 points. And then I'm going to make 4 signals: sine 1x, sine 2x, sine 3x, sine 4x. Okay? And you can also do this in MATLAB. Here's the MATLAB code that would be similar to this, which is I can make a signal, again, chop it up into 2 points and make these sine waves. So what do these look like? Well, they look like this: sine 1x, sine 2x, sine 3x, sine 4x. Okay? So these are these sine waves I'm building up. And part of the advocation here, right, is that the Fourier analysis telling us that we're going to build all our signals out of functions like this. There's also this very important assumption we're making, or that has been advocated, that these functions are in fact orthogonal to each other. Now remember, these functions, we plot them in 1D, really, but if I chop this up into 200 points, they are living in a 200-dimensional space. And in that 200-dimensional space, these things are orthogonal to each other. And I'm going to show you that, okay? Because we can actually take inner products of these, and you find that in fact the inner product of these is 0. So inner product of this vector with this vector, remember these are vectors of length 200 because we just created them right here. So this vector S1, if I take the inner product of S1 with S2, or the dot product, it's 0. S2 with S3, it's 0. S1 with S3, it's 0. Any of these combinations of vectors that you take the inner product against each other, it's 0. And so just keep that in mind, because these are now my coordinate system I'm using to represent a signal. And I made this point earlier, and Fourier has made this point, that in fact you can represent any signal in terms of these. And again, with the restrictions that we just showed right at the beginning of, here's the convergence criteria. And so let's make a code with a function that is not periodic. It's going to be a Gaussian. And then we're going to try to represent it with Fourier modes. So for instance, here's a Gaussian I can create. So take a function. It's a Gaussian because exponent minus 2 to the square of x minus pi plus 1 squared. So what we're doing is it's a shifted version of a Gaussian. I've shifted it over so it's centered somewhere else. Same thing here. So here, this is the MATLAB version. It's centered here at pi minus 1. So that's where the 0 is. And I square this thing. So this is going to be some Gaussian off center. And what I want to do then is to compute the coefficients for each of those sine waves that I'm using. So the way we do this, right, is the formulas we use for this is that if I'm doing this, I take this sine wave. If I want to know how much of that Gaussian is in the sine wave, what we do is we would actually compute this inner product here. You take your function f and you dot it with s1. And this is a1. That's the coefficient in front of the sine 1x. You can take that function f against s2, which is sine 2x, take the dot product. That is how much is in the direction of sine 2x. And then sine 3x, sine 4x. And then I can add these up to create my signal. So I'm basically saying take that Gaussian, take a dot product of it with this function, this function, this function, and this function. And that is giving me how much is in each direction of these sine waves. Okay, those are the A of k's. And that's how easy it is to compute, taking the dot product. And this is exactly what I did here in MATLAB as well. Build the function, take the dot product of f with the s1 direction, s2 direction, s3, s4, add them together. Okay? And so, in fact, you don't have to just do it into 4 functions. Here what I'm going to do is actually I'm going to project it and do a sum. Remember, the sum is infinite. It goes from negative and right. The sum is over all k values. But what we're going to do is we're going to actually just sum this up over 9 Fourier modes. So here is the little loop. For first my approximation, I'm going to start with 0. And I'm going to go into this loop and go in through it 9 times. And I'm going to make a plot here. And you'll see the plot in a moment. But I'm going to take the sines. And I'm going to take the basis function sine, create it. So this is going to be making, actually what we did here is, let's say, sine x over 2, sine x, sine 2x, and so forth. And we're going to make it of length 1. This is a normalization step. So it's just making an orthonormal coordinate system. I take the function s, I dot it with respect to each of these basis functions. That gives me the a. And then I add them together. A times s. This is the sum that represents the Fourier representation, and I'm going to plot this. Same thing in MATLAB. Here it is. Here's my sine. I normalize it to make it length 1, this vector, and then I take the inner product of the function f I'm trying to represent against this sine function. That gives me the coefficient of how much energy is in that direction, and then I add it together. And here you can start to see the convergence of what happens here. Now this is kind of a remarkable picture, so I want you to just really take a look at it. We start here. The blue is that Gaussian we're trying to represent. So it's not really a periodic function in the sense that normally you would think about sines and cosines. But what I'm going to do is try to represent that with sines and cosines. So if I used a single sine, here it is. And of course, I don't do that well of representation. That orange line is not a very good representation of the blue. But now I say, well, I got sine x over 2. Now sine x, so I have a second Fourier mode. I add them together in the right way because I projected it onto that blue. Here is the representation. Well, certainly this is better than this. Now I use 3 modes, 4 modes, 5 modes, 6 modes, 7, 8, and 9. Look at this. By the time I use 9 Fourier modes, I've done such a nice job of building that blue function. In fact, you can see how well I've done here in getting it just with 9 modes. And remember, Fourier says if I use an infinite number of modes, that orange and blue will actually converge to each other. And that's the guarantee that Fourier has. So this is why we love Fourier, because we can just take even a small number of modes, here 9, and represent these signals. And now what I have, because I have these 9 modes are eigenfunctions of the LTI system. So they're very easy to manipulate in the LTI context. And I know they work, and I can represent any function with them. So that's going to be the key idea. So you have this little bit of code. that you have available here. And in fact, on the website for this course that I will build out, you can download that code, the Python code and the MATLAB code I showed here, but at least you can go back and look at it and just copy and paste it as well. And that will finish this lecture. But I've shown you some important properties here. One is that you can show, and I showed that in the example, that this Fourier representation converges to a function that you would pick out to represent it in terms of, and I've given you the conditions under which all of this converges. So one of the things that we want to handle next, and this will happen in the next lecture, is to think about this in the context also of discrete cosine transforms, which are slightly different than the continuous case here, but we will consider that in the next lecture.